today's video, here is a nice problem. It's coming from Brazilian Math Olympiad edition 2000. Here is the following application. We have R from R to R. We have this first obvious output of f of 0, which equals 1. And we have the second application. We have f of x plus f of y equals f of x plus y plus number 1. So the question, we are going to determine all the functions which build this application. Okay. In fact, this is very nice and straightforward problem. It's not easy, it's not hard at all, but it's very important and useful function. So I'm going to talk a little bit about this one. So before we proceed with the solution, let's take an example for the linear function. If we have a linear function f of x, which equals ax plus b, okay? So we know this function is always monotonically increasing or decreasing, okay? So we can find this function is going this way like this, or is going like this, okay? This is increasing, this is decreasing, because the slope of this one is positive, the slope of this one negative, okay? So if you find the function as a linear function like this is monotonically increasing, which means is accepting inverse, okay? And the function is 1 to 1, and the function is increasing, the function 1 to 1, because if you choose two inputs here on this function, let's put this one, the first one, x2, x1 and x2. This one is a f of x2, this one is a f of x1, okay? So if you take a look, the output of this x1 and x2 are different, okay? And also f of x2 is bigger than f of x1, which means the function is clearly increasing, which means in the other word is accepting the inverse function. What's the inverse function for this one? So let's set f of x, for example, equals ax plus b, which equals y, okay? Let's take this one to the right and get ax equals y minus b. So which means x equals 1 over a, y minus b over a, okay? So this one is going to be written as a prime y minus like b prime, okay? So which means you get f of y, which equals a prime y minus b prime, okay? So the inverse of this function is 1. So let's get started with this problem. Let's put, when we have x equals y equals 0. It's very simple in order to reduce the expression to the smallest expression possible. So I'm going to replace y and x with 0 here. So I get here f of plus f of 0, which equals f of 0 plus number 1. We know f of 0 it equals 1, which means this one equals f of 1. We know f of 0 equals 1, 1 plus 1, which equals 2. So we get f of 1 equals 2, okay? Now let's go to that general expression, replace y with 0 and leave x free, okay? Let's set y equals 0, but x is free, so I get f of x plus f of 0, which equals f of x plus 0 plus number 1. So this one is giving me x plus f of 0, replace it with number 1, equals f of x plus number 1, okay? It's clearly, it seems, is going to be a linear function here. Now let's claim we have a linear function f of x equals ax plus b. Let's calculate this difference, because we have this one f of x plus number 1 minus f of x equals 1. So let's do the same thing, replacing this one with x plus number 1. So I get f of x plus number 1 equals a. I'm replacing x with x plus number 1 plus b. Let's make this difference, f of x plus number 1 minus f of x, which equals ax plus number 1 plus b minus ax plus b. Let's simplify this one. I will be ended. This one, ax will be cancelled out, b will be cancelled out. I will be left with a. We already know this difference equals 1. We have determined a as a constant. Let's replace the value of a into this one. So I get f of x equals x plus b. Let's find b, replacing x with 0. F of 0 equals b. We know f of 0 equals 1. We have determined b as well. So thus f of x equals x plus number 1. Okay. So this function already know is continuous function, continue and differentiable function, and the limit exists. We have no restrictions points, as well as the function is bijective. Okay, we have that all this function is clean. This function has no problems at all. Now we found f of x equals 1, f of x equals x plus number 1 as a linear function. Let's do the second method. So since we know a function is continuous and differentiable and the limit exists, I'm going to apply this information. Let's apply this fact on this one. Since I have this difference, so I have f of x plus number 1 minus f of x equals number 1. Okay, let's divide the denominator by x plus number 1 minus number 1. So I get here x plus number 1 minus x, as I did nothing here. So taking this x plus number 1 minus x, put it here, which is 1, equals 1. Let's remind you about a very important definition here regarding differentiability for the function. So we know the limit of f of x plus h minus f of x over h, we know have h is approaching to 0, equals f prime of x. This is differentiability definition, okay, for the derivative function. So let's apply the same here, what you have here. Let's put it on this form. So let's apply the limit on both sides. I get the limit of f of x plus h. Let's replace h. Let's replace h with number 1 here, minus f of x over x plus number 1 minus 1 is replaced with h, which equals 1. With h is approaching to number 1. So we already know this one equals 1. And also by the definition, this one equals f prime of x equals 1. Okay? Since we found the derivative function of this one equals 1, let's apply the integral on this one, on both sides. I get dx equals dx. Okay? So this function is given as f of x. This is f prime of x because you're applying the integral on both sides. F of x equals, which is f of x, and also the primitive of function of number 1 here, which is x plus another constant c. So it's very simple to determine the constant here. So since we have the initial condition here, so I get f of 0, which equals 0 plus c, which equals 1. We get c equals 1. Thus f of x equals x plus number 1. Also we found the same thing with different method. I have undo this video. By the way, don't forget to hit the subscribe button and support the channel, and thank you for watching. I will see you next video. Bye.